Hello viewers and welcome to the linear algebra series. We are on to the topic of diagonalization, and here we have a question which says that determine the values of ABC so that the two matrices are diagonalizable. Now let us quickly just have a look on the matrix A. So we have got matrix A with entries 1AB, 0, negative 1C and 0, 0, 2. And if you will observe A, then A is an upper triangular matrix. And since A is an upper triangular matrix, its eigenvalues are nothing but the entries on its diagonal. So we have 1, negative 1 and 2 are the eigenvalues of A. And since all eigenvalues are distinct, it implies that A is diagonalizable. Thus you can see that there is no condition imposed on A, B and C. So we can say that A, B, C can be any real number, and it will always imply that A is going to be diagonalizable. Now let's hop on to the matrix B. Again, for matrix B, it's an upper triangular matrix, so we have the diagonal entries to be the eigenvalue. So for B, we have 1, 2 and 2 are the eigenvalues of B. However, if you will notice that lambda equal to 1 is repeated only once. So for lambda equal to 1, the algebraic multiplicity is 1. And for lambda equal to 2, since it's repeated twice, so the algebraic multiplicity is 2. Now, if it happens that the geometric multiplicity of the eigenvalue lambda equal to 2 is also 2, then we can conclude that B is diagonalizable. So we wish to find out the geometric multiplicity for 2. So for that, we will be finding the eigenvalue for lambda equal to 2 corresponding to the matrix B. To find the eigenvector for B, consider the equation B minus 2 times I, where 2 is the eigenvalue, times x is equal to 0. Here x is the eigenvector, and this gives us the matrix negative 1, A, B, 0, 0, C, 0, 0, 0 times x, y, z is equal to 0, 0, 0. Simplifying this, we get a pair of equations, that is negative x plus ay plus bz is equal to 0 and cz is equal to 0. This gives rise to two cases from equation 2. So let us say case 1 if c is 0 and case 2 where c is not 0. So if c is 0, then we just have one equation, that is negative x plus ay plus bz is equal to 0, which is one equation in 3 unknown, and thus there will be 2 free variables. And these 2 free variables are going to give rise to 2 eigenvectors which will be linearly independent. And thus the geometric multiplicity corresponding to the eigenvalue lambda equal to 2 is going to be 2. That coincides with the algebraic multiplicity, and since both the algebraic multiplicity and geometric multiplicity coincide, we can say that the matrix B is going to be diagonalizable. And yet again we see that there is no involvement of A and B, so we can say that A and B could be any real numbers and C must be 0, so that the matrix B is going to be diagonalizable. So this falls under the case when C is equal to 0. Now let's move on to C not being 0. So in this case we have pair of equations, that will be negative x plus ay plus bz is 0, and from the second equation we have cz is equal to 0. Now since we know that c is not equal to 0, this would imply that z must be 0. And if I substitute z equal to 0 in the first equation, we get negative x plus ay is equal to 0. That gives us that x is equal to ay, and we get the eigenvector x to be, so x, we have the value for x as ay and y remains as it is, and 0. If we factor out y, we get y times a 1 0. Thus we get only one eigenvector, which tells us that the geometric multiplicity corresponding to the eigenvalue lambda equal to 2 is 1, and therefore we have that the algebraic multiplicity and geometric multiplicity are unequal, and this implies that B is not diagonalizable. Thus, if we talk about the case if C is non-zero, we will end up getting that B is not diagonalizable. And hence for matrix B to be diagonalizable, we can say that A and B could be any real number while C must be 0. So that's all in this video. Thank you so much for watching till the end and happy learning.